Okay, so now we're going to get into practical applications. Our guy D-Rad is just chilling on his little chair that I drew for him. So yeah, I shouldn't have to spend much time on E. coli because, well, you're all upper level biology students. However, I'm going to spend some time on E. coli. So as you can see, I drew E. coli here. It's a little bit bigger than D-Rad would be. D-Rad would be. D-Rad would be. Total size. E. coli's a little bit bigger at about 3 micrometers. As you can see, this is the DNA. This is the cytoplasm, and this is the cell membrane. E. coli is important. As we get into the practical application of it all, we're going to talk about some use in which E. coli and D-Rad can form a little bit of a symbiotic relationship, except for not actually symbiotic, because I don't want to confuse people. Biologically speaking, establish that you probably know enough about E. coli, but how about a plasmid? John, do you remember what a plasmid is? Okay, why don't you tell us what a plasmid is then? Circular? That's all you got? I mean, it's written right here. You couldn't just look on the board and say this. Clearly that blue dust did not help you. So a plasmid is a small DNA molecule that is physically separated from a chromosomal DNA, and it can replicate independently. And that's important when you're looking at genetics. If you guys remember that plasmids are the way that we take what we have and make what we want. I'm going to draw a quick little diagram of E. coli plasmid. This is a plasmid right here. I'm sure a lot of you remember this, if not all of you remember this from genetics. It's important to remember because D-Rad is a very, very important player in a lot of things that involve our future, one of which I'm going to get into momentarily after I explain the plasmids. The plasmid here is isolated and removed from our bacteria, and then we have this nice little round spherical, circular thing, as Sean said, to work with. And we take the DNA containing our gene of interest and we enzymatically cleave that so that we can put it into fragments. We have smaller pieces of DNA. I think a lot of us have actually done this in lab. Maybe I'm explaining things again, but again, isolate the gene of interest. A good example of this would be insulin in E. coli, recombinant DNA, so that we can treat something that we normally wouldn't have been able to treat in the time. Now we're going to move on from this and we're going to talk about bioremediation. So now we're on to bioremediation. D-Rad's construction site right here, as you can see. Bioremediation, and I broke the word down a little bit here. Remediate means to solve. So right now I'm remediating Sean's problems. Anyways, bioremediate means to solve a problem with biological organisms. You guys really should be writing this down, you know. I don't see pens moving. You should be writing this down. Last time I checked, D-Rad was a biological organism. We're going to talk about redox a little bit. This specific organism, or other organisms, breaking down of contaminants by using them as an energy source is a classic redox reaction. An energy source, an electron donor, an electron acceptor, and nutrients, of course. Now for us, we know what nutrients are, clearly Doritos, pretty much nothing else. Our electron acceptor, oxygen, without it, We wouldn't be able to live, we wouldn't be able to do anything really without our final electron acceptor. Our guy DRAD, he's anaerobic. He doesn't need the oxygen that we have, so he's clearly got to do something for that electron acceptor. I mean, if you look at us, our electron acceptor kind of right here, we'll just draw it as a circle, and there it is. That's going to be O2. DRAD here, productive growth, doesn't rely on the same things that we have. You guys got redox down? Okay. For DRAD, productive growth relies on some carbon source, nicotinic acid, a source of sulfur, a nitrogen source, and a source of manganese. DRAD right here, he's anaerobic, so without that oxygen, his electron acceptor, he needs to use something else. In his case, it's going to be the manganese. So as you can see, his electron acceptor is completely different. Now, I don't know why I just made manganese out of wood, because it's a construction site and I really don't have any clue what manganese looks like. But anyways, that's DRAD's electron acceptor, because he's a chemoautotrophic organism. And some of their electron acceptors can be a lot of things that we wouldn't even think to use that way, and that would be like nitrate, manganese, iron, and sulfate. There's a lot of possibilities with our DRAD guy. So of course, I'm going to continue on with the construction analogy, just kind of show you how DRAD could be a helpful bioremediation tool. We're going to say that this barrel has manganese in it. So what if some crazy maniac happens to be walking by this construction site and shooting bullets off all over the place, and we just get a stray bullet that comes into here, shoots a hole right in our little manganese tank here, and we start leaking manganese. Now, we don't want manganese laying all over the ground here. Manganese is toxic, but we do need trace amounts for some things. However, in abundance, it can be toxic. In fact, it's called a toxic essential trace element. So we'll just say for this illustration that manganese is horribly toxic, horribly radioactive. Keep with me here. So this is just giving off all sorts of radiation because our little manganese pile is dangerous and seriously toxic. We just hired DRAD and company to come in. DRAD uses that manganese as his electron acceptor. He uses it to gain energy for himself and cleans up the site. That is how DRAD can be impactful in bioremediation.
I'm waking up to ash and dust. I wipe my brow and I sweat my rust. I'm breathing in the chemicals.
So probably not the best drawing ever. I never claimed to be a really great artist. We're going to talk about global nuclear weapon production and testing between the years of about 1945 and 1986. Now, unfortunately, all of this did take place. It's too bad we couldn't have gone ahead first and created the particle accelerated and maybe made mini explosions to see what they did before making actual huge explosions. But the explosions that we did make left a lot of highly toxic things in our soil, in our plants. Maybe it is making a plant that's more resistant than DRAD ever will. Maybe Nick is absolutely right on this one. Our own nuclear experimenting and global nuclear testing left a lot of these three chemicals. I'm going to talk about them a little bit more in length, but that's all you need to know is these are the things that are left behind from our nuclear endeavors. Do you remember our buddy E. coli? That's E. coli. So we've got a gene in our E. coli here that comes from this plasmid that's known as MER-A. And what MER-A does is it encodes for mercuric ion reductase. That's highly toxic thiol-reactive mercuric ion. Now what the gene does is it takes that mercuric ion and it reduces it to a much less toxic, less harmful, in fact, nearly inert form of mercury. Now I know what you're thinking. What does all this have to do with DRAD? I mean, I'm spending a lot of time on E. coli here when this is all about DRAD. But as you can see, our little buddy E. coli, he absolutely has the right tools. No matter what tools our little E. coli guy has, E. coli just simply can't lift the tools. Now normally he can, however, this site is radioactive and just making his strength nothing. He can barely even touch these tools. DRAD here has all the strengths in the world. In fact, he can hang out at this site all day long. It's like a day at the beach to him. He's just chilling. So what do? How do we solve this problem? Well, we have this little plasmid right here. We're going to look at that plasmid under a microscope. In our plasmid there, we have our MER-A gene. So we take that MER-A gene, we pull it out, and we insert it into DRAD's plasmid right here. And now we have DRAD with his shiny new plasmid right there. Not only is he in his tropical situation here where he can bask in the glow of his radiation, just like he likes it, but now he's got the MER-A gene. And with the MER-A gene, he can, of course, turn the toxic mercury into the non-toxic mercury, which, if you remember, is basically inert, because he just takes these tools here from E. coli and goes to his job. Everybody benefits. He gets energy. We get it cleaned up. One thing that I hadn't told you yet, all of this nuclear tinkering, it's estimated that this will cost about $265 billion. Now, the way it was cited in the paper, I honestly can't tell if that's an annual expense or an overall expense. I assume probably overall expense, but how scary would that be if that's an annual expense? That being said, DRAD has the ability to come in, clean this place up, reduce that, and then we can put it to something a little bit more resourceful. So once again, it looks like DRAD and the cockroaches are hanging out at the end of time, based on this reality right here anyways.